Okay, so S is the set of those natural numbers k for which this property is true, or this statement is true, where A has k elements. It may be the case that, for example, when A has, there may be some A with say 3 elements for which this is not true, with some other B, then 3 will not belong to S. So what we want to prove here is that S is equal to n, which means that for all values of cardinality of k, this is true. And that actually proves this one. And you see, S by definition is a subset of n. And we want to prove that S is equal to n. If we achieve this one, that will mean that this is true for any value of cardinality of A. And we are not restricting cardinality of B. So it is anyway true for all cardinalities of B. Now, the fact that S is a subset of n and we are trying to prove that S is equal to n allows us to use the principle of mathematical induction. How? If we show that 0 belongs to S and whenever k belongs to S, then k plus 1 also belongs to S, then we are done, right? Because then the principle of mathematical induction says that S must be equal to n. And when that is true, this has been proved. So this way we can apply induction on cardinality of A. So all we have to do now is show these two things. In other words, we have to show that whenever A is having 0 element, this formula is true, and having assumed that the formula is true when A has k elements, we have to prove that it is also true when A has k plus 1 elements. Then we are through. Okay, so that is the strategy. It may seem somewhat complicated at this stage, but as you go through more and more induction proofs, it will become, you will see that it's a lot easier than it seems. So, first, if cardinality of A is 0, then A is the empty set, because only the empty set has no elements. So that's why the number of elements is 0. In that case, A cross B, we have just now proved if one of the sets in a Cartesian product is the empty set, this one, then the product itself is also the empty set, which is 0. And this product is also 0. Hence, this is equal to this. So at least in the case where cardinality of A is 0, this formula is true, which means that 0 belongs to that set S. Although we haven't written any S or anything here, we just write hence. The result is true for cardinality cardinality of A equal to 0. Now this part where you show that something is true for 0, it is called the basis of the induction. And then we have to show that if it is true for cardinality of A equal to K, then it is also true for cardinality of A equal to K plus 1. That is called the induction step. And the assumption that this is true for cardinality of A equal to K, that is called the induction hypothesis. Okay, these things will become clear as we do more induction proofs. Okay, so no need to worry about what something is called. Let us just go through the proof. Now, assume this is equal to this into this for all finite sets A comma B such that cardinality of A is equal to K, where K is some natural number. Right? K is some natural number. So this is our induction hypothesis, which we are assuming to be true, that this formula is true. Which one? This one is true whenever in place of this number we have K. You see, we are assuming that this formula is true for cardinality of A equal to K. Now, that does not mean that there is only one set A with K elements. Actually, there may be there are infinitely many sets with K elements. For example, you can have a set of K oranges, or K apples, or K protons, or any such thing, K numbers, K irrational numbers, K rational numbers. So, for all of them, this is true. And at the same time, B can be any finite set. We are not even restricting. You see, we have put a restriction on the size of K, but on the size of B, we are not putting any restriction. B just needs to be finite. For all of such B and all of such A's, this is true whenever A has K elements. This is our assumption. Now we have to prove a similar one where one of the sets, the first set, has K plus 1 elements. Okay, so this is our induction hypothesis. Now we are going to perform the induction step. So let C comma D be finite sets with cardinality of C equal to K plus 1. What is our aim? Our aim is to show this. This is what we have to show. It's not given to us. What is given is this. Okay. Note that C is equal to K plus 1, which means that cardinality of C is not 0 because K is natural number. So K plus 1 cannot be 0. The least value of K plus 1 is 1 when K is equal to 0, and it can be more than that. So we write that since K plus 1 is greater than 0, C is non-empty. 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 C is non-empty C cannot be empty because k plus 1 can never be equal to 0. So there exists an element C belonging to C. Note that we have been able to choose an element C in C because C is non-empty. Otherwise we cannot choose an element because we don't know whether C is empty or not. But because C is non-empty, we have been able to choose any element, and it does not matter what element this is. It's just we have to choose one element of C. But why are we doing that? You will realize why soon. Okay. Then, what is the cardinality of C minus C? Capital C has how many elements? K plus 1 elements. From that set, we are removing one element. So, the resulting set has how many elements? K elements, one has been removed. So, this is equal to K. So, that means this is a set cardinally, C minus singleton set C. This is a finite set having k elements, and D is any finite set. Now look at our induction hypothesis. Assume that this is true whenever A and B are finite and cardinality of the first set is equal to k. So here C and D are, this and D are finite and cardinality of this is equal to k. So by the induction hypothesis, we have C minus C cross D is equal to C minus C into D. Okay, this is coming from this induction hypothesis. Okay, but we don't want the cardinality of this. We want the cardinality of this. This is what we want, right? So how to have that? Okay, here let us take a small example. Suppose my C is 1, 2, 3 and D is suppose 1. Okay. Now what is C cross D? C cross D is, we already know how to write this set down. 2, 1 and 3, 1. Now if my small c is, small c, if you remember, small c is some element of capital C. You can choose any one of these three. Let me choose 2. Suppose c is equal to 2. Then what is this set? C minus 2 cross D. It is C minus 2 means 1, 3 cross 1. So this one will give me 1, 1, 3, 1. Right? Now you can see that this is equal to this union 2, 1. Obviously, because you can take two of them and write the third one as a singleton set. And this is equal to this. So this is equal to C minus 2 cross D union 2 comma 1. Now what is this 2 comma 1? Okay, now realize what we have done here. We have written C cross D in terms of this and something extra. This is already given to us. Okay, in the general situation we have this, and we also know what its number of elements is. But what is this extra? This extra is actually that element which we have chosen from C, and we have taken its Cartesian product with D. This part is actually equal to 2 cross 1, which is nothing but singleton set C cross D. Okay, one more thing you can see here is that this set and this set are disjoint. They don't have any common elements. Why? Because in this set, what are the elements? The elements are ordered pairs where the first coordinate is coming from C minus 2 and the second coordinate is coming from D. So the first coordinate cannot be equal to 2. Whereas in the second set, the first coordinate is equal to 2. So these two sets are disjoint, and we are taking their union, and their union turns out to be equal to this. So can you see this? It's like the situation is like this. This is my C minus C cross D, and this is my C cross D. They are disjoint, and their union is equal to C cross D. So the number of elements here will be equal to the number of elements here plus the number of elements here, right? So based on this small analysis, this is this times D. So based on this small analysis, we can write now C cross D is equal to C minus C cross D union C cross D, and C minus C cross D intersection C cross D is equal to empty set, which means that C cross D is a union of two disjoint sets. It's like this. This is C cross D. This is one set. This is another set. There is nothing common. It's the union of two. So the number of elements here is equal to number of elements here plus number of elements here. It's like having a bag of 10 oranges and a bag of 2 apples. So the union will have 12 things, 10 oranges plus 2 apples, along with 2 apples. Hence, cardinality of C cross D is equal to cardinality of C minus C cross D plus cardinality of C cross D. Now you see from here we would have already got this is equal to cardinality of C minus C times cardinality of D plus. Now what is cardinality of this? Okay, for that again let us take a small example. You see, suppose you look at this one, or since we took 2 there, let us take 2 here also. Suppose I write A, B, C. What is this Cartesian product? Here the first element of each ordered pair is constantly 2. 2 comma A, 2 comma B, 2 comma C. Okay, so you see that the number of elements in this Cartesian product is again 3. It's just the number of elements in the second set, because the first set contributes only the first coordinate in each pair and there is only one such coordinate. So it is unable to increase the number because the first coordinate is constant. So here also this is nothing but cardinality of D. This can be thought of as D. Okay. Now this is actually what? You see, this is K. K times cardinality of D plus cardinality of D. So this is equal to K plus 1 times cardinality of D. And that is equal to, I am writing from here to here, okay. Now K plus 1 is what? K plus 1 is the cardinality of C times cardinality of D. So this is what we wanted to prove. Having chosen that the formula which we are trying to prove is true, where the first set has k elements, we have now proved the same formula where the first set has k plus 1 elements. So this concludes our induction, and so this formula is true for all values of cardinality of A, and that's why it is in general true. This is an example of a proof by induction. So at the end of this you write hence or this concludes the induction. The induction and the proof. Okay, it is looking very messy and clumsy, but if you have been following me carefully, excuse me, then you have to write this at the end of the proof. Okay, so we have proved the first one. So now we know that a Cartesian product like this has how many? See, we don't even have to write the Cartesian product, write all the elements in the Cartesian product. We know this has 2 elements, this has 3 elements, so the Cartesian product will have 2 into 3 equal to 6 elements. So that is the first result. For the second one though, we will not use induction, although induction can be used, but at this level I try to prove this using basic set theory, I mean at school level. Okay. So what we do here, I will give you the basic idea, and the proof proper will be carried out later on at some point. So the idea is like this. What the result says, if we have two finite sets A and B, then the cardinal number of elements in their union is equal to the number of elements in A plus the number of elements in B minus the number of elements in A intersection B. Okay, now the thing is like this. This is A, this is B. Right? So we need some identities to prove this, some set theoretic identities or properties of sets that we have got. So for many properties we have got, something like that we need. And the things we need are these. You have to show these things for me. A union B is equal to A minus B union A intersection B union B minus A. This is one thing. Okay, so this is homework. Prove the following. This is one identity. The second one is A is equal to A minus B union A intersection B. Similarly, B is equal to B minus A union A intersection B. And the third is, these three sets are disjoint. From when we take any two out of them and form their intersection, that is empty. You see, there is no common element between this one, this much region and this one, or this one and this one, or this one and this one. That is, there is a language, there is a term which says the sets A minus B, comma, A intersection B and B minus A are mutually disjoint. That is, A minus B intersection A intersection B is empty. A minus B intersection B minus A is empty, and A intersection B intersection B minus A is empty. That is, out of these three sets, if you choose any two, they are disjoint. That's what mutual disjointness means. Okay. These are the things you have to prove. And the proof of the actual result needs these things. First of all, okay, so I am assuming that you have already proved this. Now I will use them to prove this one. First of all, you see, A union B is the union of this set. This is A minus B, this much. And A intersection B, this much. And B minus A, this much. this region. Okay, so A union B is the union of these three sets, and these three sets are mutually disjoint, that is, there is no common element. Then what do you think A union B will be? I mean, its cardinality. It is just these elements plus these elements plus these elements. Since there is no common element, there is no fear of repetition. You see, if your A is like this, 1, 2, and your B is like this, 2, 3, then A has 2 elements. So this is equal to 2. B also has 2 elements. Now if we simply add them up, I get 4, but A union B has 3 elements, and this extra 1 is coming because I have counted the element 2 twice. Once in counting cardinality of A and once in counting cardinality of B. So that means I have accounted for a single element more than once. So that's why I am getting this wrong figure for I have to subtract something, and that something is this. How that we will see. But if I had a situation like this, if I had A consisting of the two elements 1 and 2 and B consisting of the two elements 3 and 4, then of course A union B will consist of 4 elements 1, 2, 3 and 4. So we can add the number of elements as such when there is no intersection, and these sets mutually have no intersection. So that's why I can add their cardinality to give me the cardinality of their union. This is coming from the first result as well as the mutual disjointness, and you have to prove those things. Okay, so this is one thing. In a similar manner, because A is equal to A minus B, union A intersection B, and these two sets are disjoint, which means A minus B intersection A intersection B is empty. So number of elements in A is equal to number of elements in A minus B plus number of elements in A intersection B. Why? Because these two sets have no elements in common. So their union is something. So the number of elements in that union will simply be the number of elements in this plus the number of elements in this. Now from here, what do we get? Cardinality of A minus B is cardinality of A minus cardinality of A intersection B. Okay. Similarly, we can write like this: B minus A plus A intersection B. B is equal to B minus A and A intersection B. So from here we get cardinality of B minus A equal to cardinality of B minus cardinality of the intersection. We now have formulas for this, expressions for this. So you can replace them by these expressions and see what happens. So in place of cardinality of A minus B, we can write cardinality of A minus cardinality of A intersection B plus cardinality of A intersection B plus this one, cardinality of B minus cardinality of A intersection B. So two of these cancel out and we are left with our desired expression. This is the proof, but the proof is not over until you prove those things which I have asked you to prove. So please go through them and try to, they are just simply set theoretic identities. We have already proved many of them as properties. So you just have to approach in the same manner. Using principle of extensionality, you have to prove that each one is a subset of the other to prove equality. Okay, so this is the second one. And the third one is also quite interesting, and that one also there we will need induction. So the third one says cardinality of the power set of A is equal to 2 to the power cardinality of A. Right? Give me a moment. So we now want to prove this one, right? So proof. So this is the second induction proof we are going to carry out. We apply induction on cardinality of A. Okay. In the previous induction proof also we have applied induction on the cardinality of A, but this is not the only thing on which we can apply induction. As we come across more and more induction proofs of several different types, we will